Why might traveling at the speed of light not be a good idea? Well, embarking on this dizzying speed, so frequently portrayed in sci-fi movies, brings a series of challenges and dangers that may not be so evident at first glance. Today, we'll dive into the world of theoretical physics and space exploration to uncover the risks that come with the idea of traveling as fast as light. Are the depictions of ultra-fast travel in movies really possible? And what would be the consequences for space adventurers who dare to try? The answers may surprise you and challenge what we know about space travel and physics. So, if you're curious to understand why this final frontier might be much more complicated and dangerous than it seems, stay with us. Ready to unravel these mysteries? Fasten your seatbelts, and let's embark on this journey of knowledge and discovery together. One of the most alarming problems would be collisions with space particles. Despite seeming empty, the vacuum of space contains a significant amount of micrometeorites, cosmic dust, and other particles. At this unimaginable speed, even a tiny particle like a grain of dust transforms into an extremely dangerous projectile. The reason for this lies in kinetic energy, which is proportional to the square of the object's speed. When a vehicle travels at the speed of light, any object it collides with, no matter how small, can release an amount of energy comparable to nuclear explosions. This happens because the relative mass of a particle increases exponentially as it approaches the speed of light, as described by Einstein's theory of relativity. Therefore, a simple grain of dust could unleash devastating energy capable of completely destroying a spaceship. Managing these hypothetical collisions would require technologies far beyond what we currently possess. A possible solution could be the development of advanced defensive shields, capable of deflecting or absorbing the impact of high-speed particles. These shields would need to be not only extremely robust, but also capable of operating under extreme conditions, generated by the quantum and relativistic physics laws that dominate these speeds. According to Albert Einstein's theory of relativity, one of the most intriguing phenomena associated with reaching speeds close to that of light is the exponential increase in an object's mass. As an object approaches this extreme speed, its mass theoretically approaches infinity. This implies that an infinite amount of energy would be required to achieve and maintain this speed, which, with current technology and understanding, becomes a practically unattainable concept. For the human body, the implications of attempting to travel at the speed of light would be even more complicated and potentially fatal. Drastic increases in body mass could lead to a series of problems, from the inability to move due to the extremely increased weight to gravitational effects that could cause distortions in the space-time around the body itself. Moreover, the human body is not adapted to withstand such extremes of acceleration and energy, which could result in irreparable damage to tissues and organic systems. Another significant aspect concerns the metabolism and energy needs of the human body under these extreme conditions. The increase in mass would imply a higher energy demand to perform any physical activity, including basic bodily functions like blood circulation and breathing. The body would need a vastly superior energy source than any terrestrial organism can generate or consume, raising questions about the biological feasibility of such a feat. When considering light-speed travel, one of the most significant challenges that emerge is communication. At such extreme speeds, radio signals, which also travel at the speed of light, would face substantial issues, such as significant delays and potential data loss. These challenges arise because, as a spacecraft moves at such speed, the distance that radio signals need to travel increases, and any communication between the spacecraft and Earth or between spacecrafts would become incredibly complicated. These communication delays are not merely inconvenient, but represent a real risk to the safety and effective operation of the spacecraft. In situations where quick decisions and responses to changing conditions are crucial, the inability to receive or send information in real time could result in critical failures. Imagine an emergency situation where every second is crucial. A delay of minutes or even hours in receiving support data from Earth could be disastrous. Furthermore, data loss is another concern. When a spacecraft travels at the speed of light, any interference in the signal path, whether due to magnetic fields, cosmic radiation, or even the distortion of space-time itself, can corrupt the transmitted data. This would mean that vital information could arrive incomplete or unintelligible, compromising missions and crew safety. High-speed space travel, especially those approaching the speed of light, faces a critical and potentially fatal challenge related to exposure to extremely high levels of cosmic radiation. As a spacecraft accelerates to relativistic speeds, the frequency and energy of the incoming cosmic radiation increase significantly due to the Doppler effect, which compresses the electromagnetic waves in front of the spacecraft. This intensifies the energy of these waves, making the radiation more dangerous and penetrating. The effects of this intensified radiation on the human body can be profoundly deleterious. Cosmic radiation is primarily composed of high-energy particles that can damage DNA and other vital cellular structures, leading to an increased risk of cancer, nervous system damage, and a variety of other health issues that could arise much more quickly due to the intensified exposure during travel at such extreme speeds. These risks are exacerbated by the difficulty in providing effective shielding against such a broad and powerful spectrum of radiation. Besides the health risks, the structural integrity of the spacecraft itself could be compromised by the intensified radiation. Materials commonly used in spacecraft construction may degrade under continuous exposure to high levels of radiation, resulting in mechanical failures that could compromise entire missions. This would require the development of new materials and shielding technologies capable of withstanding these extreme conditions without failing. Traveling at the speed of light would theoretically open up incredible possibilities for exploring the vast cosmos. However, even reaching this astronomical speed, we would face significant limitations due to the universe's immensity. Even at the speed of light, the distance between stars and galaxies is so vast that many desired destinations would still be out of reach within a human lifetime. For instance, a trip to the nearest star to the Sun, Proxima Centauri, located about 424 light-years away, would take more than 4 years, assuming we could achieve and maintain this extreme speed immediately. Faced with this challenge, cryogenics emerges as a possible solution to prolong the viability of long-duration space missions. This technique involves freezing and storing human bodies at extremely low temperatures in the hope of preserving life until the journey is complete or until medical technology can treat previously incurable diseases. In theory, this would allow astronauts to wait during long periods without aging or suffering the degenerative effects associated with aging, making the exploration of distant destinations feasible. However, cryogenics also presents several substantial limitations. So far, the technology has not been able to successfully revive frozen humans, and there are no guarantees that the damage caused to tissues by the freezing process can be completely reversed in the future. Moreover, the longevity of cryogenic facilities and their ability to maintain stable conditions over decades or even centuries remains uncertain. Technical issues, such as power failures or equipment damage over long periods, could compromise the feasibility of reviving those placed in stasis. So, we wrap up another journey through the fascinating and often challenging world of light-speed space travel. Today, we explored everything from the risks of collisions with space particles to the complexities of interstellar communication, the dangers of cosmic radiation, and the intriguing yet still not entirely viable possibilities offered by cryogenics. These challenges highlight how much we still need to advance in our technology and understanding of the universe to transform these fascinating theories of space travel into reality. While this future is yet to arrive, we will continue here, exploring the wonders of the cosmos and pushing the boundaries of human knowledge. Don't forget to like this video, subscribe to the channel, and hit the bell so you don't miss any of our adventures. Leave in the comments what you find most intriguing about light-speed travel and what other topics you would like to see here. Until next time, space explorers.